Very good morning to Dr. Nazari and Dr. Lanovi. Today, our group 10, would like to introduce you to our thermodynamic 2 project, which have the topic of methanol dehydration process. Now I'd like to introduce the members in group 10, which is Nicole, Alvin, Karen, and Shenu. Now we'll go for the introduction of production of dimethyl ether. Dimethyl ether is a clean and versatile chemical compound which have a chemical formulas of CH3OCH3, and it's having a chemical equation of 2CH3OH, which is 2 ethanol, and it will form our dimethyl ether and plus with water. It has attracted attention for its environmental friendliness and diverse application in the industrial and energy sector. It is also a promised alternative to diesel in combustion ignition engine due to its high cetane number and absence of NOx emission and lower autoignition temperature compared to fossil fuel. DME also play an important role in the production of chemicals such as dimethyl sulfate and methyl acetate and serve as an environmental friendly aerosol and refrigerant. Now I would like to have an explanation in terms of the catalytic dehydration of methanol. Catalytic dehydration of methanol is a cost-effective and straightforward method for the production of DME by using an acid-base catalyst such as gamma alumina or zeolite. This two following equations is the equation that we use in catalytic dehydration of methanol. First, we will have a reaction between carbon monoxide and two hydrogen to form methanol, and two methanol will break down and then form 1 mole of DME and water. Even that this process is straightforward for the production of DME, but it still remain a challenge in optimizing the operating condition and ensuring the high DME yield. Now let us go to the problem statement, aim, and objective for our project. First, the problem statement for our project is to optimize the catalytic dehydration of methanol for DME production, which still remain challenging due to the significant influence of operating condition and reaction efficiency. Next, for our aim is that we're trying to use expand plus V14 to stimulate the production of dimethyl ether from methanol. And last but not least, which is our objective for our project, first we're trying to analyze the variable which affecting DME yield by varying the refractory column fixed stage and also the distillate flow rate, which is kg per hour, through a detailed simulation. And also, we're trying to achieve a high productivity, purity, and process efficiency. The stimulation result will be analyzed to determine the optimum operating condition. Next, I would like to pass to my colleague to have a detailed explanation on the methodology of our project. Thank you.
Hi, I'm Yi Seng Yu, and now I will talk about the methodology of this project. The diagram here shows the process flow diagram of the methanol dehydration process in SPM plus B14. For the design of the simulation of the methanol dehydration process, the feed material, which is methanol, is preheated before entering the reactor. The reactor product was processed to a cooler in order to lower the temperature before feeding to the refractory distillation column. The refractory distillation column was used to remove the methanol water mixture from dimethyl ether. Dimethyl ether was removed from the top stream of the refractory, while the methanol water mixture was removed from the bottom of the refrigerant as byproduct. In this simulation, there are three components in this simulation, which are methanol, dimethyl ether, and water. The property method chosen was NRTL, non-random to liquid. In this simulation, the feed stream contains of 99% of methanol and 1% of water, which has a molar flow rate of 262 kmol per hour with a temperature of 25 degrees Celsius and a pressure of 100 kilopascal. The heater that used to preheat the feed material was operated at 225 degrees Celsius and 1480 kilopascal. The return where the dehydration reaction occurred was operated at 360 degrees Celsius and 1480 kilopascal. The cooler that used to cool the return product was operated at 20 degrees Celsius and 3 atm. For separating the product, the refract distillation column was designed to have a total of 10 stages, including the condenser and reboiler. The distillation rate of refract was set at 4,500 kg per hour, while the reflux ratio is set at 0.045. The feed stream was designed as the stage 5 of the top stage, while the pressure of the refract was set at 1.8 atm.
Now, I will talk about the discussion of our report. First thing first, let me introduce again the chemical reaction that involved in our process line. So the chemical reaction is that the methanol will convert into dimethyl ether and water. So the chemical equation is shown in the top of the slide, which is 2 molecule of methanol will convert into 1 dimethyl ether and 1 water. Next, let us move on to the properties of reaction. So since this is a exothermic reaction, the change of the enthalpy is always negative. We can see from the graph at the left hand side here. So this graph shows the change of the Gibbs energy, the enthalpy and the entropy when varies the temperature. As you can see here, the change of the enthalpy is always negative since it is exothermic reaction. And when the temperature increase above 525 degrees Celsius, the Gibbs energy become positive, which means that it is a non-spontaneous equation and is not thermodynamically preferable. So next, the reaction will shift to the left at the equilibrium when the temperature increase. This can be proved by the equation at the bottom here. So when the temperature increase and the change of the enthalpy is negative, the value of the right hand side will become negative, which means that the equilibrium constant K will decrease when the temperature increase. Next, let me talk about the process line that we stimulate using the S-band plus. So first thing first, a feed stream with pure methanol will enter the heater, which allowed the preheating process until 225 degrees Celsius. After that, the hot feed stream will transfer into the reactor, which set as 360 degrees Celsius. So as I mentioned just now, since this is the exothermic reaction, so this reaction is not preferred to occur in the high temperature as its equilibrium constant will decrease, which means that the less product will be produced. However, we still choose the reactor to be 360 degrees Celsius, which is quite high because we want to supply more heat to the molecule in order to overcome their activation energy. As we can see from the graph at the left hand side, in order to carry out certain reaction, the molecules need to absorb enough energy to overcome its activation energy. So when the temperature of the reactor is higher, which means that the molecule are able to absorb energy and overcome the activation energy at the highest rate. Next, from the graph here, we also can see that after the molecule achieving the activation energy, then need to release some heat in order to form the product. So in order to create a better environment for the heat releasing process, we will transport the product stream to the cooler. So the cooler is set as 20 degrees Celsius, which is much lower than the temperature of the product stream, which is 360 degrees Celsius. So the huge temperature difference between the cooler and the product stream allowed the molecule to release heat to the surrounding. And this also increased the production rate of the DME. Next, the another function of the cooler is actually produce a vapor liquid mixture for better separation in the reflect. For information, the boiling point of the DME is negative 24, which means that it will always maintain in the gas stage, where at the 20 degrees Celsius, the water will maintain its liquid state. So the liquid and vapor mixture is better for separation process in the reflect. However, the vapor liquid mixture is have some difficulties when during the transportation because the mixture might cause the pressure drop and it is quite difficult to handle. So we will suggest that the cooler can be set as 100 degrees Celsius, which means that both DME and water can maintain in the vapor stage, vapor stage, which is much easy to be transported. After that, the cool product stream, which contain the leftover methanol, dimethyl ether, and the water, will enter the reflect. In the reflect, we will study about two major parameters, which is how the feed stage and the distillate rate affect the productivity and the purity of the DME at the top product of the reflect.
Now I will talk about the major parameter. One of the major parameter was determined as the feed stage. From the result summary, when the distillate rate is 47 at 9.47 kg per hour, stage 2 has the higher purity and productivity when compared to other stage. But theoretically, if the feed introduced too high, it will cause the limited use of upper stage and lower DME purity. If the feed introduced too low, it will cause ineffective use of lower stage, potentially causing unreacted methanol or water to remain in the product. For the energy and cost consideration, if the higher feed stage was used, it will increase pump energy consumption, thus higher operational cost was used. So, stage 5 represents as a balance point where the feed enters a region with the correct vapor-liquid equilibrium for efficient separation and minimize energy consumption. Next, the major parameter will be the distillate rate. According to the 3D graph, distillate rates ranging from 1000 to 5500 kg per hour shows that the DME flow rate increased with higher distillate rates. How does the distillate rate affect the purity and yield? If the distillate rate used is too high, the separation time will be reduced and lower the product purity as more unseparated components in distillate. If the distillate rate used is lower, it will improve purity through thorough separation. And if the rate is too low, it can lead to reduced overall yield and cause excessive recycling within the column. So, optimal rates such as 4,700 kg per hour can be used to maintain high purity, minimize energy consumption, and balance reboiler and condenser duties.
Now, let's move to the conclusion of this project. In this study, the methanol dehydration process was simulated by using SPM plus B14 software. The methanol dehydration process is the exothermic reaction, where the temperature of the reactor will affect the production of dimethyl ether. To optimize the process, there are two main parameters, which are feed stage and also distill rate of the red frog. These two main parameters are varied in order to obtain an optimum condition for the production of DME. From this study, the optimal condition for the production of DME is when the feed stage of the red frog is intermediate, which is around stage 5, and also when the distill rate is around 4,700 to 4,800 kg per hour. In this study, there is still methanol content in the bottom string of the red frog distillation column. So the unconverted methanol can be recycled back to the system to improve the overall process efficiency. And also, a heat exchanger can be used as the heat from the exothermization can be used for preheating for the feed stream in order to decrease the energy consumption and also increase the overall energy efficiency. That's all from us. Thank you.